Last class we learned the well-architected framework, and one of its 6 pillars was reliability and A212 POLF. Does your system keep working when things fail? Today, we take that pillar and make it concrete. We answered the practical question. How do you actually build a system that stays up, even as its parts break one by one? That property has a name, NAD81, high availability, often shortened to HAA and AT8081, and it is one of the most important things a cloud architect designs for. Here is the mindset shift that makes it click. In the cloud, at scale, failure is not an exceptional event, it is a constant. Servers crash, disks die, networks drop, whole data centers occasionally go dark. If your system depends on nothing ever failing, it will fail, because something always does. High availability is the art of designing so that these inevitable failures do not take your users down with them, NAA212, so that when a component dies, the system quietly keeps serving, and no one even notices. Today you will learn the core techniques that make this possible, eliminating single points of failure, adding redundancy, balancing load, spreading across zones, and failing over automatically. These are the building blocks of every dependable system in the cloud. Let us learn to stay up. Here is our path for today. First, what availability actually means. Second, single points of failure. Third, redundancy. Fourth, load balancing. Fifth, zones and automatic failover. And sixth, measuring availability in nines. Let us dive in. Let us begin by defining availability precisely, because a clear target shapes everything that follows. Availability is the fraction of time your system is up and correctly serving its users. If your service works whenever people try to use it, it has high availability. If it is frequently down or unreachable, it has low availability. It is usually expressed as a percentage of time up over some period, an 80-100 tool. And as we will see at the end, small sounding differences in that percentage mean very different amounts of downtime. High availability, then, is not about preventing every failure and 80-12. That is impossible and 80-12, but about designing so that failures do not translate into downtime for your users. The goal is continuity of service. A component can fail, a server can crash, a disk can die. What matters is that the system as a whole keeps serving requests despite that, so from the user and E39's point of view, nothing went wrong. Availability is measured at the level of the whole service, not the individual part. This reframes the whole engineering problem. Instead of the hopeless goal, an A2 PAR6, make sure nothing ever breaks. An A2 PAR6 high availability sets the achievable goal, an A2 PAR6. Make sure that when something breaks, the system keeps working anyway. NA201, that shift, NA200-212, from preventing failure to tolerating NA200-212, is the foundation of everything in this class. You assume parts will fail, and you design a whole that survives their failure. Every technique we cover today is a way of achieving exactly that. So the takeaway, availability is the fraction of time your system is up and serving users. And high availability means designing not to prevent every failure, and 800-12, impossible, and 800-100, but so that when a part fails, the whole system keeps serving anyway. The goal is continuity, measured across the whole service. To build a system that survives failure, you first have to find the places where a single failure would be fatal. Those are single points of failure. A single point of failure is any one component whose failure brings down the entire system. The one web server that, if it crashes, takes your whole site offline. The one database that everything depends on. The one network link connecting you to the world. If the whole system rests on that single part continuing to work, then that part is a single point of failure, and A212, a lurking guarantee of an outage, waiting for the day that component inevitably fails. The essential discipline of high availability is to hunt these down. You look at your architecture and ask, component by component, a simple brutal question, NAD200, if this one thing fails, does the system go down? NAD201, everywhere the answer is yes, you have found a single point of failure that must be addressed. This is often revealing an 82-12 systems that seem robust frequently rest on one unduplicated database, one load balancer, one critical service, quietly holding the whole thing up alone. Numbing them is powerful because it turns a vague worry and A212, A201, will they stay up, and A220 and A201 into a concrete checklist. Here are the exact paths that can each kill us, and here is what we will do about each one. And the answer to a single point of failure is essentially always the same. The technique that is the heart of high availability stops depending on any single one of anything. Which brings us to redundancy. So the takeaway? A single point of failure is any lone component whose failure downs the whole system and 8212, the one database, the one load balancer, and 8212. And the core discipline of HA is to hunt them by asking an 8212. If this fails, do we go down any A2 and then eliminate each one, almost always through redundancy? Redundancy is the single most important idea in high availability, and it is the direct cure for single points of failure. Let us understand it well. The idea is simple. Run more than one of every critical component. Instead of one web server, run several. Instead of one database, run a primary with one or more replicas. Instead of one of anything your system depends on, have two or more. You are deliberately building in duplication and 8012 spares that exist precisely so that no single component is irreplaceable. The effect is exactly what high availability needs. If you have 3 web servers and one crashes, the other 2 are already there, still serving an A202 the system keeps running, just with a little less capacity, and users notice nothing. The failure that would have been an outage becomes a non-event because a healthy copy was standing ready to carry on. Redundancy converts an A200 at 1. This part failing takes us down an A200 at 1 into an A200 at 1. This part failing is absorbed by its backups. This is why redundancy is the cure for single points of failure. By definition, a component you have duplicated is no longer a single point of failure because it is no longer single. Every place you found a lone critical component in the last step. Redundancy is the fix, and 8, 212 add a second, a third. So no one of them is holding the system up alone. It does cost more to run multiple copies, of course, and that is the price of availability, but for anything that must stay up, it is the foundational investment. Almost every other HA technique is really a way of making redundancy work well. So the takeaway, redundancy means running more than one of every critical component. So when one fails, a healthy copy is already serving, and users notice nothing and A212. It is the direct cure for single points of failure, since a duplicated component is no longer single. And it is the foundation the other HA techniques build on. Redundancy gives you multiple copies and A212, but something has to distribute work across them and steer traffic away from any that fail. That something is a load balancer. A load balancer sits in front of your redundant servers, and all incoming requests arrive at it rather than at any individual server. It is the single front door that then decides, for each request, which of your several servers should handle it. This solves the immediate practical question redundancy raises. If I have 5 web servers, how do users and AT9 requests get spread across all 5 rather than piling onto one? The load balancer is the answer. Its first job is exactly that distribution. It spreads the incoming load across all the healthy servers, so the work is shared and no single server is overwhelmed. This is where the AN 8 to 1 26 balancing 826 in the name comes from. AN 8 to 1 12. It keeps the load even. But its second job is the one that matters most for availability, and it is beautiful in its simplicity. The load balancer continuously checks which servers are healthy, and it only sends traffic to healthy ones. The moment a server fails, the load balancer notices and simply stops routing requests to it, and A202 powers. It routes around the failure, sending everything to the servers that are still working. Users are seamlessly served by the healthy servers and never even know one died. So the load balancer does double duty. It shares load across your redundant servers in normal times, and it automatically hides failures by avoiding dead servers. It is the piece that turns a pile of redundant servers into a smooth, self-healing front end. So the takeaway? A load balancer sits in front of your redundant servers as a single front door, spreading incoming requests across all the healthy ones, so no server is overwhelmed and 82 worlds. And crucially, it checks health continuously and routes around any failed server, so failures are hidden from users automatically. Redundancy has a subtle trap. Copies only protect you if they cannot all fail at the same time. Solving that is what availability zones are for. Imagine you run 3 redundant servers, but all 3 sit in the same physical data center. Now that data center loses power or floods, or its network is cut, all 3 of your servers go down together, and your redundancy was worthless and 812y, because the thing that failed took out every copy at once. Redundant components that share a common fate are not truly redundant against that shared risk. This is the trap. Duplication in one place does not protect against that place failing. The fix, which you met back in the regions and zones class, is to spread your redundant copies across availability zones and 80 SWOT whole. Separate, isolated data centers within a region, each with its own power, cooling, and networking. Put one server in Zone A, another in Zone B, another in Zone C. Now the failures that would take out a whole data center and 82-fold, power, flood, fire, and 82-fold, only affect one zone, and your copies in the other zones keep serving. You have made your redundancy resilient against even a complete data center outage. This is a crucial refinement of the redundancy principle. It is not enough to have multiple copies. Those copies must be independent, placed so they do not fail together. The general rule is to spread redundancy across failure boundaries and 85 tuple across zones for data center failures, and for the most critical systems, even across regions for whole region disasters. The more independent your copies, the larger the disaster your system can shrug off. Redundancy plus independence is what real high availability is built on. So the takeaway: redundant copies protect you only if they can in 39 T fail together. So you spread them across availability zones and 8205 separate data centers with independent power and networking and 8205, so that even a full zone outage leaves copies serving in other zones. Redundancy must be independent to be real. We have redundant copies spread across zones with a load balancer in front. The last piece is the automation that detects a failure and reacts to it and 8200 poll with no human involved. That is health checks and failover. Health checks are continuous, automatic tests of whether each component is alive and working properly. At regular intervals and 81200 every few seconds and 81200, the system pings each server or service and asks, in effect, and 81200, are you healthy? And 81200 I1, a component that responds correctly, is marked healthy. One that fails to respond or responds with errors is marked unhealthy. This constant monitoring is the sensory system of high availability. It is how the system knows, in near real time, the state of every part. Failover is what happens when a health check detects a failure. The system automatically switches away from the failed component to a healthy one. The load balancer stops sending traffic to a server that failed its health check. If a primary database goes unhealthy, the system promotes a replica to take its place. The redundant copy that was standing by is brought into service automatically, and the system carries on. Failover is redundancy plus health checks in action, and 80-1, the detection triggers the switch. The word that matters most here is automatic. The entire value of this machinery is that it works in seconds, at any hour, with no human needing to wake up, notice the problem, and intervene. A failure at 3 in the morning is detected and routed around before anyone is even paged. That is the difference between a system that is highly available and one that merely has backups someone has to scramble to activate. Health checks watch constantly. failover reacts instantly, and together they make your redundancy self-driving. This is the culmination of everything today: redundant, independent copies, fronted by a balancer, monitored by health checks, with automatic failover and 8200, a system that heals itself. So the takeaway: health checks continuously and automatically test whether each component is alive, and failover automatically switches from a failed component to a healthy standby the moment a check fails, and 8200 is. The key word being automatic. So failures are detected and routed around in seconds, at any hour, with no human needed. Availability is something we can actually measure and promise, and the way it is expressed, and A209, 209, 209, 209, 209, 209, 209, A209, 209, is worth understanding because it reveals how demanding real reliability is. Availability is quoted as a percentage of uptime, and people talk about the number of nines. 99% is an 8200, 2 nines, 8200, 8200. 99.9 is an 8200, 3 nines, 8200, 8200. 99.9, 99 is an 8200, 4 nines, 8200 ARN, and so on. These sound almost identical, and A220 fall. They are all NA220, basically 100% NA220 fall, and A220, but the difference between them, measured in actual downtime, is enormous. And that is the point everyone must internalize. Let us make it concrete. 99% availability sounds great and 80 hen to palvi, but it means your system can be down about 3.5 days per year and still hit the target. At a 99.9%, allows only about 9 hours of downtime a year. Another 99.99%, permits under an hour and A212, about 52 minutes and A212 for the whole year. Each additional 9 cuts the allowed downtime by roughly 10 times. What looked like a rounding difference in the percentage is actually the difference between days and minutes of outage. And here is the crucial engineering reality: each extra 9 is dramatically harder and more expensive to achieve. Going from 2 nines to 3 might just need basic redundancy. Getting to 4 or 5 nines demands multi-zone and multi-region redundancy, sophisticated automatic failover, relentless testing, and eliminating every last single point of failure. This is why availability targets are a real business decision, often written into service-level agreements and A200 to how. SLAs and A200 to how. The formal promises providers make about uptime. You choose your target based on how much downtime you can tolerate versus how much you are willing to invest, because every additional 9 costs far more than the last. Match the 9s to what the system truly needs, and A212, no more, no less. So the takeaway: availability is measured in N8200 nines and 8220, and each extra 9 cuts allowed downtime roughly tenfold, and 8200 200. 99% is about 3.5 days a year, 99 200 200 is under an hour, and 8200 200, while each 9 is far harder and costlier to reach. So the target, often fixed in an SLA, is a real trade-off between tolerable downtime and investment. Before we recap, let us clear up a distinction that often confuses people: the difference between high availability and disaster recovery. They are related, but they are not the same thing. High availability, everything we have discussed today, is about surviving the everyday, expected failures, and A202, a server crashing, a disk dying, even a zone going down, and A200 202, with no downtime and no human intervention. It is automatic, it is continuous, and its goal is that these routine failures never become visible outages. HA is your defense against the failures that happen all the time, keeping the system serving right through them. Disaster recovery, by contrast, is about recovering from rare, large-scale catastrophes. An 8212, a whole region destroyed, a catastrophic data corruption, a major security incident, and 800 212, events so severe that they overwhelm your normal high availability design. Disaster recovery is a separate plan built around backups and the ability to restore your system often in a different location after such an event. It is less about zero downtime and more about being able to come back at all and how quickly after the worst happens. The keen way to hold the distinction. High availability keeps you running through normal failures with no downtime. Disaster recovery brings you back after an abnormal catastrophe. HA is a live automatic property of your running system. DA is a plan and a set of backups you hope never to need but must have. A serious system needs both. An I2128, HA for the daily reality of component failures, and DR for the rare day something truly catastrophic happens. They complement each other, covering the full spectrum from a single crashed server to a lost data center. Designed for both, matched to what your system can tolerate. So, the takeaway, high availability survives everyday failures automatically with no downtime, while disaster recovery is a separate plan built on backups and restoration to bring you back after a rare catastrophe that overwhelms your HI design, and 8 HHA keeps you running through normal failures. DR brings you back from disaster, and serious systems need both. Let us gather the whole class in one breath. Availability is the share of time you are up, and high availability keeps serving users right through failures. A single point of failure is any one component that can down everything, and A212, find them and remove them. Redundancy is the cure, run more than one of everything critical, so a failure has a backup ready. A load balancer spreads traffic across your servers and automatically routes around any that fail. Spread redundant copies across zones and let health checks trigger automatic failover to a healthy copy. And availability is measured in nines and A212. Each extra 9 means far less downtime and far more effort. Next class, NAI212. Scaling, growing to meet demand automatically, one idea at a time. That is high availability.